Okay, so we'll get into the table in a sec, but how many? Well, we'll just go around the room. I'll just jot them all down. How many did you get correct? 2. Okay, so I'll just jot it down here. I'll make a little table. Number correct. All right, Josh. 1. Sam?
0.
None? You did not study.
Oh, just 1.
1.
3.
3. All right. Obviously, you did the reading.
1.
1. 2. 1. Alex, did you have a chance to do it? No? Okay. Yes, sir.
5. I have 3.
3?
I got
2 and 1? Okay.
You got 0.
Okay, so based on this, what we can do is we could actually make a determination of some probabilities. So I'll get to number 2 in a second, but number 3, it's asking us the probability of getting exactly 2 questions correct. Experimentally, what we'd be looking at would be the number of trials. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the number in which, or the number of cases in which there were exactly 2 correct answers. Okay, so that happened 3 times. So we would conclude that the probability would be 3 out of 11. Obviously, if we increase the number of trials, what we would get is something that's closer and closer to the true probability. All right, but going back to number 2, it says, is this a binomial setting? So the binomial part of it is really addressing the fact that there are 2 possible outcomes. Ooh, slipped. All right. Now, you might look at it and say, well, there's 4 possible outcomes, A, B, C, or D. But the 2 outcomes really just boils down to the idea of being correct or incorrect. All right. So how we define our variables is really important because you can pretty much take anything and make it binomial. Like, for example, annual salaries. You would think, well, how could that be considered binomial? If you create a benchmark and you say, okay, either your salary is over 50,000 or under 50,000, for example, all right? In which case you've just taken really infinitely many possibilities and just dialed it down to 1 of 2 possibilities, all right? So here we're looking at something that it's based on randomization to some extent, but you know, there's also a systematic approach taken in some places. So, Evan, you use the classic strategy of picking a choice and going with it if you had no idea? Yeah.
I knew I'd get at least 1 right. Or not.
Well,
I was really likely to get at least 1.
Right, it would help because if you start fluctuating your choices, then you could be consistently fluctuating away from the distribution of the solutions. But if you know that there's going to be some sort of varied distribution of the choices, you know, like if you had, let's say, 300 questions, you know, you could conceivably determine that like roughly somewhere in the neighborhood of 75 would be choice A, 75 would be choice B, and C and D also 75 at the top, roughly. Right? So, but it would fluctuate itself back and forth throughout the possible choices. So if you fluctuate, you could actually come up with like, let's just say it's a trigonometric wave that somebody was using. They're just doing it in the form of a sine wave. You could actually end up cosigning your way away from getting anything correct. All right, so that would be pretty terrible. But if you come up with a fixed value and work your way straight through using that, odds are it's going to oscillate back and forth through your line, but you wouldn't expect to get too many correct. All right, so some of us we've got 3 out of 4, so 75 just by guessing, but it's only 4 questions. So what we would want to do, obviously, is make a determination of what the probabilities would be without having to run a simulation, without having to actually figure out individual probabilities, and then use, multiplication rule, addition rule, things like that, there's got to be a shortcut, and there actually is. All right. So, but it does come into the idea of having a binomial distribution. If you know it's binomial, then the techniques I'm about to show you come into play. All right. So, number 4, fill in a table showing the probability of getting exactly X correct. Right. So, and this is based off of our data set. All right. So, yeah, and I'll show you how to do this, using the calculator in a little bit. But they're all out of 11. And we're just counting up the number of instances in which a person got none of them correct. Right? Oh, sorry, there were 5 questions, so the 3 is 60%, not 75%. I misspoke earlier. That happened just the one time, right?
Go.
5 times for the ones. 2 we figured out already is 3. 3 happened twice. Nobody got 4 out of 5 or 5 out of 5 correct.
Has anyone ever gotten all 5 correct on this activity?
Yeah. Yeah, just straight up dumb luck. But it's fun. So find and interpret the mean of the distribution. So this is where we pop all this stuff into our calculators. All right, so stat, edit, 0 through 5. I got way too much in there, so let me just clear them out. So 1 out of 11, 5 out of 11, 3 out of 11, 2 out of 11, and then a couple of goose eggs. All right, so we're looking to find the mean and standard deviation. Easy enough. Stack calc 1, list 1, list 2. For my list and frequency list. A little calculation there. So we're looking at about 1.545-ish if I'm rounding to 3 significant. So I'll just make a note of that for now. And we'll talk about the interpretation in a minute. 1.545. The standard deviation, we're looking at about 0.891. On your calculators, it just leaves the S blank. So you really can't, when you're looking for the standard deviation of a probability distribution, you really can't screw it up, because as long as you type in the data correctly, you're not going to accidentally select the wrong type of standard deviation, because it's just flat out not going to give you an S. All right, so it's just going to be the lowercase sigma. So that's good news. All right. Then we could get into probabilities and things like that. But what this is telling me is the expected value. All right. The mean of a probability distribution is the expected value. In this context, it's talking about the number we expect to get correct. Okay. That was, I don't know what that was. I don't even know what I hit in order to make that happen. All right. Now, the standard deviation of 0.891 is talking about the spread of the data. All right. So how much dispersion or how much variation there is in data. Now, the data is specifically talking about the number of questions correct. Related to the number correct. All right, and so we can make a determination of certain things like, what would be usual versus unusual. All right, so if I take the 1.545 and add to it, let me put out of here, 1.545 and add to it 2 times 0.891, and then do the same thing with subtraction. I would figure out the usual, unusual interval. It's really just the addition that matters, though. All right, so you know they weren't really calling for it in this case, but it's nice to throw it in there. Unusual to get more than 3.327 correct. Again, they didn't call for it, but I would want to know that. I about to take a test and I didn't study. I got like an hour prior to the test. Do I study or do I play it out and see how things go? All right, just take a shot in the dark. Just start guessing. All right. Here it's saying that that it would be extraordinarily unusual, but just unusual to get more than 3.327 correct. Right. So I'm not expecting, and if you do the math on that, 3.327 out of 5, so that's 33.3 out of 50. So you're talking about 67%. Right? So basically saying it would be unusual to get a passing grade just by guessing. Right? So mathematically, I mean, intuitively, we always knew we had to study, but this is a mathematical justification for it. Right? But you might look at this scenario and say, well, it's only a 5-question test. I've never had a 5-question test before. Right? What's the benefit of this kind of problem? I've never had a 5-question test before either, but I have had 100-question multiple choice tests where I did not know how to do 5 of them. Right? So 95 out of the 100, I'm good. The last 5, I had no idea. So what this is telling me is that for the ones that I have to guess on, it's giving me a sense of the probabilities. All right, now this is all still experimental. We have not figured out anything related to what it ought to be for real cases. So let's continue on just with the experimental approach. Probability of getting at most 3 correct. So x has to be less than or equal to 3. So 1 plus 5 plus 3 plus 2 all over 11. So we're really, really doubling down on this idea that, like, yeah, you got to study for multiple choice assessments because this is not going to, like, all this is saying is at most 3 correct is talking about the probability of failing, right? So it's a certainty based off of these this collected data. Probability of getting 3 or more correct, right? So probability that x is going to be greater than or equal to 3. That's going to be 2 plus 0 plus 0 out of 11. So 2 out of 11. All right. So not good. But what we want to do is take this and come up with a generalization for it. And that's something known as the Binomial Theorem. So in your packets on page, we could also use our calculators to determine the correct distribution. All right. In order to do that, very, very easy. All you have to do is put everything in to the Binom PDF except for an x value. All right. So just type in Binom PDF 5, 1/4. All right. 5 trials, probability of success 1/4, and then hit enter. And it will figure out the probabilities for every outcome going from 0 to 5, all right? 0 to whatever your end value is, which is a really nice feature because now if I wanted to find, if a question said find the mean and standard deviation of a binomial distribution, I could do it very, very easily, right? Because I could store this information in, right? So speaking of which, I would just hit store and I'd pop it into L2. Actually, I'll put it in L3 because we typed in our experimental values. So hit enter, store it into L3, hit enter, and now when you go into your stat editor, you could see side by side, we have what we came up with experimentally and what the calculator is saying the probability should have been, right? In either case, we're getting something that is, very likely for the low values of X, but then it starts getting less and less likely as you go on, all right? So not too crazy, but we could also find the mean and standard deviation of this. So I could do stat calc 1, L1 against L3. And so this is what the mean and standard deviation should have been. All right.
We weren't too far.
Was that?
We weren't that far.
We weren't too far away. At least for the mean. So 1.25 and 0.968 should have been. All right. So, for small values of X, N, you could expect a fair amount of variation. But as you increase the number of trials, your probabilities start tightening up. And so you will get lower and lower as you, or at least approach the variation will get smaller and smaller as you increase the sample size. All right, so that's that. Now, a nice question would be, all right, well, how could I have figured out those numbers, the mean and standard deviation, without having to do all that work? Right, because I don't want to come up with an entire distribution just to find the mean and standard deviation. So a little bit of a spoiler, because it's on the next page of your notes. For a binomial distribution, mu is equal to NP, and sigma is equal to the square root of NPQ. This is binomial only. All right, so very easy to verify this because my number of trials was 5. My probability of success is 1/4. I just realized I was blocking like the view of half the class by sitting there. So, so 5 times 1/4, 1.25. Now for the sigma, I would multiply that by 3/4 probability of failure, and then take the square root. And I get my 0.968, all right? So this is a more convenient way of doing it because then you don't actually have to worry about coming up with an entire distribution just to do this, just to find the mean and standard deviation. That being said, if for whatever reason you blank on what the formulas are, which you shouldn't because it's on the AP formula sheet, you can always just invent it. All right, but you still have to remember something, and that something would be how to figure it out on the calculator in terms of the entire distribution. You can do something very similar to this one, 22. We'll actually go through the algebraic techniques. Well, I won't go too crazy with the algebra because a lot of it is intuitive. So. Ah, dang it, typo. Given 5 multiple choice questions, each with 4 choices. Why not?
Yeah, I did too.
All right, so the issue here is that we gotta really think about not only getting 2 questions correct, but also the number of ways in which you could get 2 questions correct. So I'm going to forget about the 4 choices here for a second, but and really only consider the idea that I have 5 questions and I'm looking for the probability of getting exactly 2 correct. If that's the case, my possibilities kind of work themselves out. I could maybe get the first 2 correct and the last 3 incorrect. That's one way it could happen. Maybe I got off to a bad start and my first 3 were incorrect, but then the last 2 were correct. All right. Maybe it was just the first one that was incorrect, then I had a little streak there where I got a couple right, and then the last 2 were incorrect. Maybe the first 2 were wrong. Then I got a couple correct, and then I got the last one wrong. Right, maybe it was the first and last values that were correct. The ones in the middle were incorrect. Maybe the first was right, the second was wrong, the third was right, then I got the rest wrong. Maybe the first was right, then the next 2 were wrong, and then the next one was right, and the last one was wrong. Alternating. How many do I have? 7. All right, there's more. All right, so let's see what else. What else would I have?
I see.
I see. So come on. See.
I see.
Yeah.
That sounds like a stutter.
Yeah.
And that's 10? All right. I was on the lookout for 10 possible arrangements here, or 10 possible actual combinations, because I have 5 things taken 2 at a time. All right. Now, if I want to just evaluate the first case, what I would do is using independent events, because you're going to have 4 choices no matter how many questions you're working on. I would find the probability of getting one correct, which would be 1 out of 4. The second one correct. Then the remaining 3 would all be incorrect. So 3/4 3 times. All right. So ultimately, if you look at each of the possibilities, you could see it has the same ingredients. Same number of correct, same number of incorrect. So this ends up being 1/4 to the second power, 3/4 to the third power. All right. Now, if I just take that 10 and multiply it by those fractions, 10 being the number of different ways in which you could have 2 correct and 3 incorrect, then I would get my actual probability. So 10 times 1/16 times 27 over 64. So 270 over 512? No?
1,000.
Off by a factor of 2. All right, so something in the neighborhood of roughly 30%. So not too good, but then again, it wasn't really an ambitious goal, right? To get only 2 questions correct out of 5 available. Now, I think it's pretty obvious that we don't want to have to do this every time. I think it's also obvious we didn't really need to do this one time either, because once we figured out what the probability was for one case and then determined the number of cases, we were good to go. So this actually is the binomial theorem, given in its most general form is NCX, p to the x, q to the n minus x, x being the number of successes, p probability of success, and q probability of failure. So you'll see this on your AP formula sheets, in a very similar fashion, except the q will be represented as 1 minus p, right? But it means the same thing, all right? So we could have just jumped right to that formula and said 5C2, probability of success on any one trial would be 1/4 to the second, then 1 minus 1/4 to the 5 minus second power. And so you get the same value that way. So 270 over 1024. All right. So that's a shortcut. But there's even a shorter shortcut. A shortcut to the shortcut, if you will. So in the vars menu, the one that we would use to find normal CDF and inverse norm, if you scroll down, so second vars, you scroll down, there's one that says binom PDF. It should be option A. Select that. You get it in menu form, right? But it's asking for the n value, the p value, and the x value. All right, so here I'm just looking for, n is the number of trials, so 5 trials, probability of success on any one trial, and the number of successes that I'm looking for. All right. So binom PDF. Right, so what we can do is go back and compare because this is what it should have been. If I had, instead of 11 people in the class, if I had 1,100 people, right, maybe split up over a bunch of different classes to collect this data, my probability of getting exactly 2 successes would have been closer to this number than it was. We got 2 over 11, which was about 0.181 or 182. It's not terribly far away, but it's far enough away that it would cause a little confusion as to what the probability would be. All right. Now, to that, to help you make a determination of. So, number 2, or example 2, is talking about the probability, and again, same typo, 5 questions, 4 choices. Find the probability of getting at most 2 correct. All right. So at most 2. Is really the same as saying x is less than or equal to 2. You could use the table, the one that we just created, and just add up values, but there's other ways to do it. All right, I'll show you another technique in a sec. This is the same as probability of getting 0 or 1 or 2. There's a function in your calculator, binom CDF. C stands for cumulative. So what I would do here is I would type in 5, 1/4, and 2. This will return the sum of all values less than or equal to 2. This finds the probability. It finds the probability of x less than or equal to x, some known value of x. All right. So second bars, it's right below binomial PDF. So option B, 5, a quarter, and 2. So about 0.896. All right, and so that's what this is detailing here, right? Because the alternative to that is to go into your stat editor after you have the distribution and add these three. Well, let me scroll up. Add these three probabilities together. All right, 0, 1, and 2. You'd have to add these together in order to get that result. Not difficult, but if there's an easier way, why not? All right. The thing is, it's not like normal CDF where you can select a range of or an interval of values. You can go to the left, you can go to the right, you can go in between. This is specifically values to the left of a given x value, less than or equal. All right. So if I want to find fewer than 2 correct, what I'd have to do is make an adjustment. All right, because by doing binomial CDF, I'm getting less than or equal to 2. All right, so binomial CDF. All right, less than or equal to 2 is what I would get if I put this in. So I don't want to do that. If I want fewer than 2 correct, then it would be a 1. So 5, 1/4, 1. Which would be the sum of the first 2 values here. So the computation isn't that bad one way or the other. So about 0.633. All right. And again, just going into the table, if you were to add these two numbers together, yeah, it looks like we'd be in that neighborhood, about 0.633. All right. So if I needed to find the probability of getting more than 2 correct, right, or more than, or at least 2 correct, I'd have to make adjustments based off of the fact that this is only going to give me less than or equal. I'd have to do some subtraction from 1.
Yeah. Q is the opposite of
Q is the opposite of P. All right. This question actually goes back to the mean and standard deviation would be. So that's what I'm going to ask you to do for homework, is answer this question, and I want you to use formula. Use the formulas and a table approach.